So I want you guys to take the next 3 to 5 minutes and do the do now, which is 1, 2, 3, 4, 5, and 6. So today we're introducing logarithms, which is a new operation, just like multiplying, dividing, adding, subtracting, or raising something to a power. This is a new operation we're going to learn. The do now is going to help us introduce it. So I want you guys to pause the video now and complete 1 through 6. So, if I look at number 1, if I want to completely simplify number 1, we have 4 over 5 to the negative second. The main thing here is we have a negative exponent. Whenever we have a negative exponent, we have to make it positive in order to completely simplify the expression. So, I want to flip the base. My base is 4 over 5. So I'm going to flip that to have it become 5 over 4, and by flipping it we now have a positive exponent, so that'll be 5 over 4 to the second power. Now further simplifying it, 5 over 4 to the second power would be 25 over 16. You could do that one of two ways. You could make it 5 squared over 4 squared, or you could do 5 over 4 times 5 over 4. So number 2, very similar question. We have a negative exponent, but here it's a little bit more difficult to see what to flip. So what I like to do for this base is, instead of writing it as 2, I would write it as 2 over 1, because it's easier to see what we're flipping if you write as a fraction. So 2 over 1 to the negative fourth, that is equivalent to, we flip the base to 1 over 2 to make that a positive exponent. And then 1 over 2 to the fourth, 1 to the fourth is 1. 2 to the fourth is 16, 1 over 16. And the last one, number 3. Here our exponent is 1 over 2. Now remember, whenever we have a fractional exponent, the 1 is our power, so 4 to the first. That 2, the denominator, is our index, which is our number on the square root. The root. It's not always going to be a square root. It could be a cube root. Could be a fourth root. But in this case, it is a square root because our denominator is a 2. So that would be the square root of 4, which is 2 for our answer here to simplify it. So for 4, 5, and 6, we are algebraically solving each of the following. So for number 4, it says 64 equals 4 to the x. We want to find out what x is. This is the basis of logarithms. So we want to find out what x is. We have to get x by itself. If I were to solve this algebraically, how would I get x by itself? We don't know how to do that yet. That's what we're learning. With this lesson. So what we have to do right now is we have to say, okay, kind of like guess and check. 4 to what power is 64? So I would do. Let me check 4 times 4. So 4 to the second. 4 to the second, 16. Let's multiply by another 4. 4 to the third, that would be 64. You could check that in your calculator too. So we know 4 to the third would equal 64. So our answer would be x has to equal 3. That's what a logarithm's doing. A logarithm's going to tell us what the exponent's going to be. It's the inverse operation of raising a base to a power. So when we do logarithms, we're gonna be able to get that x by itself when we do this algebraically. So let's keep on going. Let's do number 5. Number 5. So this one's a little bit different. It's not just plain old 4 to the x, or 8 to the x in this case. We're multiplying 8 to the x by 5. So in order to get x by itself here, we have to first divide by 5 on both sides to get that x by itself. 2,560 divided by 5, that should be 512 equals 8 to the x. Okay, remember these 5's cancel, that's why it's 8 to the x. 8 to what power is going to give me 512? Well, I know 8 times 8, which is 8 squared, gives you 64. Let's multiply by 8 again, 8 to the third. That's going to get me 512. So 8 to the third is going to equal 512. So I know my exponent there, my x, which we're trying to solve for, is going to equal 3. And the last one, number 6. So same sort of thing, divide by 2 on both sides because we want to get the x by itself. Divide by 2, divide by 2. These two cancel over here, so it'll be 40 equals 3 to the x. Let's keep on going. Kind of guess and check to see what our x is going to be equal to, like we did above. 3 to the first, we know that's 3. 3 squared is 9. 3 to the third is 27. We haven't got 40 yet. 3 to the 4 is equal to 81. None of those equal 40. So how do we know what it's going to be? Well, I see here 27 and 81. I know it's got to be in between these two numbers. What's my exponents here? The 3 and the 4. So I know my x value is going to be somewhere between 3 and 4. I don't know exactly what, though. So we know it's estimated between 3 and 4. I'm going to estimate it. I don't know. I'll say it's 3.5. Just for a quick estimate. But that's where logarithms are going to come into effect. So we're going to be able to use a logarithm to get x by itself. And then we're going to be able to find the exact answer to this equation. So what we're going to be able to know by the end of the day is I can explain how to perform a logarithmic expression. I can calculate or estimate logarithms without using a calculator. I can convert equations between logarithmic and exponential form. I can find the inverse of an exponential equation. I can graph a logarithmic equation, and I can show and explain how a logarithmic function is the inverse of an exponential function. And I can't stress this enough. I really want you guys, once we get to figuring out how to do logarithms in the calculator, to only use your calculator to check your answers. Don't use your calculator to find the actual logarithm, unless it asks you to find the exact logarithm. It's a question like number 6 where we have to estimate it and then check. I want you guys to really not lean on your calculators for this, because you will be able to understand it much better if you don't lean on your calculators for this. On the next page, so this is when we're really going to delve into the idea of a logarithm. So I'm going to do it the first one with you guys, and I want you to do the next 5. So the idea of a logarithm is really, it's asking you to find the exponent. So essentially what the exponent is asking is, how many times of one number do we need to multiply to get another number? So for example, how many times do I need to multiply, I don't know, 2 to get 8? Well, I need to multiply 2, 1, 2, 3 different times. So 2 to the third to get 8. So that's what we're going to be doing here with these questions. So when the problem asks us how many times do I multiply 8 by to get 64? Let's take a look at that. So 8, let's first do 8 times 8. 8 times 8, that does give you 64. So how many times do I need to multiply 8 to get 64? That was only 2 times. So that would be our answer, 2 times. You could also say 2, that's fine too. Think about that as 8 squared equals 64. We multiply it twice. 8 times 8, you multiply 8 times 8, so 2 times, to get 64. I want you guys to do the next 5 and pause the video, take 3 to 5 minutes, and play it once you are completed with those 5. So let's take a look at that second one. That second one is, how many times do I multiply 3 to get 81? So I'm going to show my work over here. 3 times 3. That gives me 9. We don't have 81 yet. Let's do 3 times 3 times 3. That gives me 27, not 81. So we multiply by another 3. 3 times 3 times 3 times 3 is really 9 times 9, if you want to look at it that way. That gives you 81. So how many times did I multiply 3 by to get 81? Well, I did it multiply 3 4 times. We could also write that as 3 to the 4th equals 81. So we're trying to find the exponent here, and I'm going to show you guys the next answers. So here are the rest of the answers. You get how many times do I have to multiply 2 by to get 256? That'd be 2 to the 8th, so we have to multiply 2 8 times. And this is all just, I just kept on multiplying, like in the fourth case, I kept on multiplying 4 until I got 1,048,576, which was, I had to multiply 4 to the 10th power to get that. And then we are going to have some negative exponents here. We're going to have some fractional exponents also. But in this case, we have a fractional base. So we're also going to have fractional bases. So 1/3, how many times do I have to multiply 1/3 to get 1 to the 27th? What I like to think of for this one is I multiply 3 different times to get 27. So 1 to the 3rd to get to 1 over 27 would be 3 times also. And then let's take a look at this last one. So 7 to the, how many times do I multiply 7 to get 45? So how many times do I multiply 7 to get to 45? Well, I did 7 to the 1st, which is just a plain old 7. And I did 7 to the 2nd, so 7 times 7, and got 49. Neither of those are 45, so we know 45 is in between 7 and 49, so that means our exponent has to be in between 1 and 2. We don't know what it is exactly yet. My estimate was 1.85. We'll see how far off I am, but we know it has to be, and since 45 is pretty close to 49, we know that our exponent should be much closer to 2. So let's take a look at what the logarithm is. So the logarithmic with base b. That's to just say logarithm with base b. Let me fix that real quick. Logarithm with base b. So logarithm with base b. Suppose b is greater than 0 and b is not equal to 1. For x is greater than 0, there is a number y such that log of base b of x is equal to y, if and only if b to the y is equal to x. So that is the definition of a logarithm. We're going to break that down a little bit more. So if we take a look at, let's take a look at the exponent first, because the exponential equation is what we know. So let's look over here at the exponential equation. And so we look at b. And if you look at b, what's b called again? B's the base. So b is what we call the base. And look at where b is in the logarithm. That's the base for the logarithm is that tiny little subscript right there. That's where the base goes when we convert from between exponential to logarithmic form. Remember, logarithm, it is the inverse function or the inverse operation to raising it to an exponential. So that is also why when we try and get the exponent by itself, there's our exponent. It is y. That's why when we perform a logarithm on the exponential function, when we convert it from exponential to logarithmic form, we get the exponent by itself. So that is why the exponent is all by itself on one side of the equation. And then the very last part is that x. That x, new vocab word here, is called the argument. And that goes as the number So if you look at the base, this is how I look at it. The base is you write the base smaller for the logarithm. It's like a subscript, and then the argument is you write the argument larger, like you would a normal number. How I remember where everything goes with the logarithm? Well, I remember the base is that tiny subscript, and then the exponent, since logarithm's the inverse operation to an exponential, I know I'm trying to get the exponent by itself, so that is why our exponent here is by itself. And then what's left over is the argument, and that goes right here. Now you may be asking yourself, how do I say this? So how would I say that log expression right there? It would just be log. How do I say log base b of x equals y? It would just be log base b of x is equal to or equals, you could say, y. And I can't stress this enough. Logarithms are the inverse property or inverse operation of exponential. Therefore, logarithms get that exponent alone on one side of the equation. So whenever you perform the logarithm, when you convert from exponential to logarithmic form, the exponent is always by itself on that side. That's how you would get that exponent by itself. If you remember back to number 6 here, how would I go about solving this? I would get to this step here. I would get to the 40 equals 3 to the x, and then I would perform a logarithm, which we're going to do later on. So I want you guys to take a second, but before you guys go off and do the top, I want to show you guys how to do number 1, and also how to do the calculator. So for each of the 6 questions above, I want you to put each of them into an exponential equation, and then convert that exponential equation into its equivalent logarithmic equation. And I want you to also check your logarithms, check your answers in the calculator to see if you get the same answer that you would. You should, and once again, I only want you to check using the calculator. I never want you to actually perform it using a calculator, unless it's one kind of like, that last one we did, how many times do I multiply 7 to get to 45? First estimate it, then go ahead and plug that in the calculator, because you're not going to be able to get that exact number without plugging into the calculator. So let's look at the first one. How many times do I multiply 8 to get 64? If I want to put that into an exponential equation, that would be 8 to the second equals 64. So that would be my exponential, but let's break that down into a logarithm. So if I were to convert that into a logarithm, that would be log. And then our base on the logarithm is the same as our base on our exponential. Base is 2, so it'll be the base is 8, so it'll be log base 8. And then I always go, I know it has to equal the exponent. So my exponent here is 2, so it equals 2. And then my argument is what my exponential is equal to, which is 64. And that goes there. So how do you say that? That would be log base 8 of 64 is equal to 2. So what that essentially is saying is, what's the exponent on 8 in order to make it equal to 64? And that would be 8 to the second. So I just want you guys to do the next 5. If you want, we can go over the second one before you do the next 4. Or you can pause it here and do the next 5, just in case you want to check the second one. Let's do the second one also. So the second one would be... I forgot to show you guys how to plug that in the calculator. So log 8 of 64. Let me show you how to plug that in the calculator. So if you have a TI-84, what you want to press is, you might think, oh wait, I see that big log button right next to 7. I'm going to press log. That's not what you want to press. So we're going to be using this in a couple days. Just plain old log means log, and the base is has to be 10. See how here we have a base of 8? We don't want to use log because that just gives us an automatic base of 10. We're going to get, if you're confused by that, don't worry. We're going to do that in a couple days. But to get a log with any base, you want to press math, and then you want to go all the way down to log base. Now, if it's crossed off, your calculator is in test mode. You want to get that out of test mode. And you can look that up online. You would need another calculator, TI-84, out of test mode to do that. It's pretty simple once you have that. But you press log base, and then our base is 8. Our argument is 64. And we know our answer should be 2 because that's our exponent on the 8 that we would need in order to get it equal to 64. Answer's 2. So it's a great way of checking. And let's do that second one now. But first, you might have a different calculator, so I want to show you guys TI Inspire also. So TI Inspire, you can look for the log, look at 10 to the x right above, that's log. So press Control, 10 to the x, and this automatically gives you the log of any base. So it'd be log of 8, base 8, sorry, of 64. This should equal 2, which was our answer. Equals 2. Awesome. So in case you're here looking, need a little more help and want to do the second one also, that's fine. So let's do the second one also. That would be, how many times do I multiply 3? So that would be 3 to the 4th equals 81 would be our exponential form. And then if I want to put that into log, it'd be log. The base on a log is the base and the exponent, log base 3. We know we're getting the exponent by itself, so it should be equal to 4 our log, and then our argument is 81. And once again, you can check that in your calculator. I'll just do it with the TI-84 this time. So that would be math, go to A, log base 3 of 81. Enter, we get 4. So 3, the exponent on our 3 is a 4 in order to get 81. So if you didn't pause the video now and try the next 4. So here are your answers for the next 4. Log base 2 of 256, and you see I put the exponential. You guys might have actually done the exponential work already when you're trying to figure out how many times 2 would multiply to get to 256. So here's the exponential for each of them, exponential form for each of them. I'll underline them in blue. So here's the exponential form for this one right here. So that would be the logarithm form for each of those. That last one, as you can see, the base is 7. Let me undo that so we can undo that circle so we can see that. The base is 7. The argument's 45. We don't know what the exponent is, so this is when you want to definitely check with your calculator. So you do math, log base. Our log base is 7 of 45 because 7 doesn't multiply by itself evenly. Get to 45. It'd be 7 times 7, or 7 squared, which is 49. That's not even 45. So if I were to round it, it would be around 1.96. So I rounded it as an answer here. X is about 1.96 for that. So we're going to continue to work with this. I want you guys to go to the next page. So on the next page, this is just a checkpoint. I want you guys to do all 15 of these. Just to make sure you're good with converting in and out of exponential form and logarithmic form, and also evaluating and estimating logarithms without a calculator. But there's one thing I want you guys to do that I think is going to help you out a lot. Before you go about this, let's just on the top write the conversion for exponential equations to logarithm equations, and logarithmic equations for exponential equations at that fact. So if we have b, the base, to the x, which is the exponent, equals y, which is the argument, that is equivalent to our logarithmic would be log Our base is still the same. Our base is b on the exponential, so our base for the logarithm is b of... I always fill out, actually, I wait for the of. I always fill out the exponent first because I think it's easier to remember. So we get the exponent alone because logarithm's the inverse operation of an exponential. So it should equal our exponent, which is x. And then our argument, which in this case is y, would go there. So that is our conversion for between exponential and logarithmic. I just want you guys to do the next 15. Pause this. It's going to take a little bit. Pause it, 5 to 10 minutes. And do these 15 questions. So here are the answers for 1 through 8. We'll go over some of them. So I want you to take a look at them. So some of the key ones I want to go over are ones that they look a little different. So let's look at number 9. We don't want like 9 before, but I just want to make sure we're good with it. So number 9, it is log base 1 of 1/5, log base 1/5 of 125th. We want to evaluate that, so let's say it's equal to x. And so if I want to figure this one out, I'm going to first put it, because I think it's easier to think about an exponential form. So I'm first going to put this into exponential form. So that would be our base is 1/5. So 1/5. Our exponent is what the log's equal to, which we don't know yet. That's what we're trying to find, which is x. Is equal to 1 and 1/25. If you think about it, let's try and draw a little thought bubble here. How do I get that 5 to equal 125? That would be 5 to the third is equal to 125. So, if that's how I get 5 to equal 125, then 1/5 to the third is going to equal 125. So my x in this case, the logarithm would be equal to 3. So 11, what's kind of different about 11 than the other ones we've done? If you look at our base is 6, and then our argument is 1 over 36. So not only is our base getting smaller, it also appears to be getting flipped. So instead of 6 over 1, it's now 1 over 36. So if you notice that, that's telling us we need to have a negative exponent, which means this logarithm is going to be negative. So that would be, it's going to be equal to some number x, so that would be 6 to the x is equal to 1 over 36. So I know we're going to have a negative exponent. We got to have that 6 flipped. How am I going to get 6 to equal 36? Well, I know 6 squared is going to equal 36. So how do I get that flipped? So it's 1 over 36. That would be 6 to the negative second equals 1 over 36 in order to flip that 6. So this logarithm would equal -2. Let's take a look at number 12. So number 12, we have log base 49 equals 7. So I know that's going to be, we'll say it's equals x. So 49 in this case is our base. We don't know our exponent, so we say it's x. That's equal to 7. Well, we're getting from 49 to 7. What's going to be my exponent here? I got to make the number get smaller. So in this case, we're actually going to be rooting 49. So what root would I take of 49 to get to 7? Well, it'd be the square root of 49 to get 7. And how do I represent the square root as an exponent? That would be 49 to the 1/2 would equal 7. So log base 49 of 7 would be 1/2. If you guys take a look at, so 13, I estimated that one to be around 2.5. Check in your calculator. There'd be 2.54395931063. 3. And I rounded it at the very end. If that was part of a problem, you want to keep it like that to the very end. But I rounded it because we were just trying to estimate that actual logarithm. Look at number 14. Very similar to number 12. How did we get from 64 to 4? We had to root it. In this case, it wasn't a square root. The square root of 64 would give you 8. We need 4, which is our argument. So it would be the third root, or the cube root of 64. So that's why x is equal to 1/3. And I look at 15, and I think 15 looks difficult, but it's deceptively not that difficult. So if we set it equal to x, because we don't know what the logarithm is going to be, so I set it equal to x. I know my base is 11 to the x equals the 6th root of 11. How can I write the 6th root of 11 as an exponent? Well, that would be 11 to the x equals 11 to the 1/6. And bam, look at that. If x is to the 1/6, then if 11's to the 1/6 and 11's to the x and they're equal to each other, well, then x has to equal 1/6. So our logarithm is equal to 1/6. So, a lot of you might be thinking, when do we use logarithms? Really, when we use logarithms, where'd that go? When do we use logarithms? So we use logarithms mostly as the inverse of an exponential. So we use it as the inverse operation of exponential. You'll also see it used with exponential growth and decay. You'll see it used with interest in banking. You'll see it used all over science. I know the pH scale is based off of it. A lot of economics is based off logs. So there's a lot to do with logarithms in the future. This is probably your first time seeing them. But, oh, whoa, look at that. Look at that bottom left corner. That's my favorite band. Has anyone seen them before? They're a really good band. I don't know if anyone's seen them before, but they would be... They're the Logarithms. They're actually a pretty oh, there it is. Yeah, it's my favorite band. It's Logarithms. They're I think that's right there. That guy is, I believe, he played at my friend's wedding. And that is the lead singer. That's Logarithmic. Mike. He's a lead singer and lead percussionist. He's pretty good. Yeah, so that's pretty much that's a good checkpoint for logarithms. Let's go to the next page. So I want you guys to take like 1 to 2 minutes and find the inverse of the following function. Pause the video if you haven't. So whenever we're trying to find the inverse of a function, you have to first understand how to find the inverse of a function. So the very first thing we have to do is you have to first swap the x and the y because they're inverses. So I'm going to look at the function we have here, which is y to the 7x, and I'm going to swap the x and the y. So instead of y equals, there's going to be x equals, it's going to be x equals 7, not 7 to the x, but 7 to the y. So I swap the x and the y, and then we don't really ever leave it x equals unless it's, x equals 1, and we're just drawing a line x equals 1. So we want to solve for y here. So the y here is the exponent. So how do we get the exponent by itself? What's the inverse operation to an exponential? It's what we're doing, the logarithmic, so it'll be log. The base is the same as the exponent, so it'll be log base 7. It's going to equal our exponent, which is y, and then our argument, which is x. So that is the inverse function of y equals 7 to the x. So what I want you guys to do is right below this. I want you guys to take, a minute, and now we're going to look at the graph of a logarithm as compared to the graph of its inverse exponential function. So I want you to find the inverse of y equals 2 to the x. Pause the video if you haven't. So it'll be the same thing as above. Find the inverse. You swap the x and the y, so it'll be x equals 2 to the y. Solve for the y. That'd be log. The base stays the same, 2. Equals the exponent. And it'd be log base 2 of x equals y. This is not the same as converting from what we did on the previous page, from a logarithmic equation to exponential. Those, it would be the equivalent equation on the other side. This is specifically finding the inverse. So we're first swapping the x and the y and then solving for y. So this is, it's a little bit different. And we're doing this so to prove that this is actually the inverse operation. So on the side of axes, you should have just learned the exponential unit. So where we graphed exponential equations. So I first want you guys to take a couple minutes and let's graph y equals 2 to the x. So take a minute and graph that. So when you're graphing this, I already filled the x's for you. So this, to find the corresponding y, when x is 0, that would be 2 to the 0 power. Remember, anything to the 0 power. Let me write that again. So it'll be 2 to the 0. What's 2 to the 0 equal to? Anything to the 0 power is equal to 1. So that would be 0, 1. So you'd come over here, plot 0, 1. And then same thing, we're going to do 2 to the first, you get 2, so it'll be 1, 2. So we're going to plot this, and you just keep on doing that. 2 to the second is 4, so it'll be 2, 4. So you just want to keep plotting that till you have the nice exponential 2 to the. So it should look like this. Make sure you label your line. So before we go about graphing the inverse, let's look at the domain and range. So the domain, remember, it's all possible x's. Domain is all possible x's. So x's go left and right, because that's the x-axis, goes left and right. So we want to look at what's the lowest possible x this goes to. Well, it keeps on going to the left, so it's not stopping anywhere. So that domain, it's from negative infinity. And then if I look at how far it's going right, this is going to keep on going. It goes pretty steep, but it keeps on going up, but it also keeps on going right. So that's not going to stop either. So that would be negative infinity to infinity. But take a look at the range. If you look at this, it's actually never going to cross the x-axis. So it's never going to cross this x-axis here. So the domain, the lowest it's going to get is just before 0. So we don't include the 0. So it'll be 0. But as you see, it's going up all the way up. So it's not stopping there. So the range is all possible y's. It's not stopping when it goes up. So it'd be from 0 to infinity. And that pink line is the asymptote. Remember, the asymptote is where the equation doesn't cross. So that doesn't cross at 0. And is that y or x equals 0? Well, the y is never changing there, so that'll be the y equals 0. So that is all the information for the exponential. Now let's take a look at the inverse function of it, which would be y equals log base 2 of x. Now remember the inverse function. What was the very first thing we had to do to find the inverse function? We had to swap the x and the y. Same goes with points. We can just look at the points for the y equals 2. Here's y equals 2 to the x. And we'll do this one for y equals log base 2 of x. All we have to do is swap the x and the y. So if the point for y equals 2 to the x was 0, 1, for its inverse function, it'd be 1, 0. And then 1, 2 would now be 2, 1, 4, 2, 8, 3, and 16, 4. And we just would plot each of those now, and this would be its inverse logarithmic equation. Not the equivalent, but its logarithmic equation. with the inverse to it. So that'd be 1, 0 would be here. 2, 1 would be there. 4, 2 here. And 8, 3 is the only one that's going to fit on this. So it's going to look like this here. But then you might be asking yourself, how is it going to look as after 1? Because you may also look in your calculator. So let's quickly graph this also. Let's quickly graph this. So if I go to y equals, and I press math, I go to log base, you might be looking, I want to see the points. So this was 2 to the x. It looks like that in your calculator. You can check the table out to get the points, as you would see. Oh, but at 0, there's an error. That's because there's an asymptote there. But how is it going to respond as it gets close to that error? So, I don't know. Let's try when x is 1/2. So when x equals 1/2, let's plug it into the equation. Y equals log base 2 of 1/2. 1/2, so that would be 2 to the y equals 1/2. And, well, it's getting flipped, so I know my exponent's going to be negative, and that 2's not changing at all, so y is going to have to equal, the exponent's going to be equal to -1. So that point would be 1/2, -1, and I'll plot that. 1/2, -1 would be there. And if you kept doing that, you would see this line would get closer and closer to the y-axis, but never actually cross, similar to how the y equals 2 to the x was getting closer and closer to the x-axis, but not crossing. And that's what it would look like. You can verify that. I know your calculator, this is always kind of confusing. The calculator, if you graph in your calculator, the calculator cuts it off. I think it's only, that's because it's like pixelated. This is still going down, but the calculator cuts it off unnecessarily because of the it's pixelated. So let's take a look at the domain and range for this. So the domain is how far left and how far right it's going. How far left this is going is, if I look at the leftmost part of this graph, it's right here. It's never going to cross 0. So it's going to be right after 0. So 0, comma, and it keeps on going on and on to the right. So 0, comma, infinity. The range, it keeps on, it goes all the way down. The range is all the possible y's, and it's going up at a very slow pace, but it's still going up. So it'll be negative infinity to infinity. And the asymptote in this case, it's the y-axis, but the y-axis, if I put it as an equation, would be when x is equal to 0. And I want you guys to take a look at this. Look at the domain and ranges and asymptotes for y equals 2 to the x and its inverse function, y equals log base 2 of x. You see that the domain, or all the x's for y equals 2 to the x, is the range, or all the y's for log base 2 of x. And then similarly, all the domain for the log equation is the same as the range. The y's and the x's are flipping. Even the asymptote, y equals 0, now x equals 0. So that is further showing that that is the inverse function. But I want you guys to take a little bit and take like 2-3 minutes. I want you to explain how the XY tables prove that the functions are inverses, and also how the graph proves that the functions are inverses. So pause it now, and we'll go over this once you press play. So if you look at the XY tables, for each corresponding point, the x and y are flipped. So if you look at 0, 1, for example, look at 0, 1, in its inverse function, it's flipped to 1, 0. Look at the last 4, 16. It's flipped to 16, 4. So for each corresponding point, the x and y's are flipped. But how can you also show it graphically? That's why we showed it graphically here. So graphically, if one function is reflected over the y over x. You get the line y equals x. You get its inverse graph or function. That's what's happening here. So the curve of y equals log base 2 of x is a reflection of y over y equals 2 to the x over the line y equals x. And that's what's happening here. You see, I drew the line y equals x for you guys to see it. It is clearly getting reflected over that. So that's it for this lesson. If you guys, I would highly recommend the next page is the success criteria. So if you can do all of these, you should be pretty good with the lesson that we went over today. I would also highly recommend the classwork. So you could be like, oops, there's the answer to the classwork. But the classwork is here to really make sure you understand the material. So you can be like, oh, I just did the success criteria. I'm good to go. This classwork's here to make sure that you guys really like remember this after today. So it's really to make sure that you put this into your long-term memory. So I would also make sure you do this classwork. Yeah, that's it.